Salam, peace be upon you. My name is Muhammad Laiq Siddiqui, the father of Holophase. Part 13. Interference Productions. When waves write patterns together. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are journeying through Book 9.3 of Episode 9, The Generative Grammar. Our exploration of wave and field generation has built a powerful foundation. We began by learning the rulebook, the dispersion relation that dictates which pure wave tones, which omega k pairs, are allowed in a given medium, like the resonant notes of an organ pipe. Then we learned how to write localized sentences, wave packets. We saw how a single raindrop splash, a mixture of many allowed tones, evolves predictably, its peak moving at the group velocity, its shape spreading according to the curvature of the dispersion curve. We have so far mastered the grammar of solitary waves, but the universe is rarely solitary. It is a chorus. Light from two slits overlaps. Sound from two speakers fills a room. Ripples from two stones cross on a pond. Today in Part 13, Interference Productions, when waves write patterns together, we enter the realm where waves meet. This is where the simple linear grammar of phi reveals a breathtaking capacity for creating complexity, structure, and information from pure overlap. Our anchor image is the surface of a quiet pond at the exact moment when two thrown pebbles have each created a set of expanding circular ripples. Stand and watch. The two wavefronts move toward each other. Where a crest from the first meets a crest from the second, the water rises even higher, a towering peak of constructive interference. Where a crest meets a trough, the water flattens out, a still line of destructive interference, a silent node amidst the motion. This meeting does not create chaos. It writes a new, stable, beautiful pattern of alternating bright and dark lines, an interference pattern. This pattern is not a property of either set of ripples alone. It is a collective creation, a sentence written by two wave sentences speaking simultaneously. Today, we learn the grammatical rule that allows this, the principle of superposition. And we discover how this simple rule, applied to the cyclic holophase field, generates the intricate lacework of reality, from the stripes of light in a double-slit experiment to the beating of your heart and the binding of atoms. Here is the elegant puzzle of this part. We have two valid wave patterns in the phi field, each a grammatically correct sentence according to the dispersion relation. What happens when both patterns are present in the same region of space at the same time? Does one erase the other? Do they collide like billiard balls? Or does the language provide a rule for combining them into a new, equally valid pattern? And if so, what are the properties of this combined pattern? The answer is the heart of linear wave physics, and, as we will see, the gateway to quantum mechanics. The rule is superposition. In its simplest form for our audio minds, it states: the total phi field at any point in time is the sum of the individual phi fields from all sources, with careful accounting for the cyclic nature of the phase. We can write this symbolically for two waves as phi total equals phi1 plus phi2, though we must remember phi is an angle, so this sum wraps around the circle. This is not a physical collision. It is a grammatical combination. Each wave proceeds as if the other were not there, but their values at each point in spacetime add together. From this deceptively simple rule, everything about interference emerges. The key is the phase difference. Because phi is cyclic, what matters is not the absolute phase of each wave, but their relative phase at the point of meeting. If they arrive in step, both at a crest or both at a trough, their phases align. This is constructive interference. The total amplitude is enhanced. If they arrive perfectly out of step, one at a crest, the other at a trough, their phases oppose. This is destructive interference. The total amplitude cancels, ideally to zero. For our holophase field, this cancellation means the total phase at that point becomes ambiguous, which often corresponds to a node of zero intensity in the wave's energy or intensity pattern, which we can think of as a tally of how intensely phi is changing. The resulting pattern, the spatial map of where constructive and destructive interference occur, is called an interference pattern. It is a fingerprint of the relationship between the two waves. Change the path length of one wave by half a wavelength, and you flip crests to troughs, turning a bright fringe dark and a dark fringe bright. This sensitivity is why interference is such a powerful tool for measurement, from detecting gravitational waves to imaging individual molecules. Let's explore the triunity of interference productions. The time echo of interference, rhythm of beats. When two waves of slightly different frequencies, omega-1 and omega-2, overlap, the interference pattern itself becomes dynamic in time. The points of constructive and destructive interference move. What you hear is a beat. The combined sound waxes and wanes at a rate equal to the difference between the two frequencies. This is the time echo. Interference generates a new rhythm, a metapulse born from the marriage of two original pulses. In the heart of a laser, this beating of modes can generate pulses of light femtoseconds long. In your brain, the interference of neural oscillations is thought to underpin cognitive rhythms. Time itself gains a textured pulse from wave interaction. The space echo of interference. Frozen geometry of fringes. For waves of the same frequency, the interference pattern is static in space. It paints a permanent landscape of peaks and valleys. In the double-slit experiment, this is the iconic pattern of bright and dark bands on the screen. In a crystal, the interference of X-ray waves from different atomic planes creates the diffraction pattern that reveals the crystal structure. The space echo is this standing tapestry of light and dark, a spatial structure that encodes information about the sources, their separation, and the wavelength. It is geometry written by wave physics. The motion echo of interference, guiding and shaping waves. Interference doesn't just make pretty patterns, it directs energy flow. In regions of constructive interference, the intensity, the energy tally, is high. In regions of destructive interference, it is low. This means the wave's energy is channeled, like water flowing along specific paths. This is the principle behind waveguides, like optical fibers, antennas, and resonant cavities. The motion of wave energy is choreographed by the interference conditions set by boundaries and other waves. The motion echo is this orchestrated flow, where the superposition rule acts as the conductor, determining where the wave's intensity can and cannot go. Now let's locate this profound node on the master tree. We are on the interference and coherence branch within book 9.3, Waves and Fields. This branch depends fundamentally on the linear superposition principle, which itself rests on the linearity of the underlying wave equations derived from phi. It also depends on having well-defined waves with stable phases, which links back to dispersion and packet generation. It enables the next critical leap, the formation of coherent fields. When many waves not only interfere, but lock in phase over extended regions and times, they create lasers, superfluids, and Bose-Einstein condensates, states of matter where quantum interference becomes macroscopic. Interference is the bridge between single waves and collective ordered fields. To ground this in experience, let's light our lanterns across the scales. A near lantern from sound. Two loudspeakers playing the same pure tone. Walk around the room. You will notice something strange. In some spots, the sound is loud and clear. In other spots, just a few steps away, the sound almost vanishes. These are acoustic interference fringes. The sound waves from the two speakers travel different paths to your ear. Where the path difference is a whole number of wavelengths, they arrive in phase and reinforce. Where the path difference is a half wavelength, a whole number and a half, they cancel. The silent spots are not magic. They are the grammatical necessity of destructive interference, a direct consequence of phi total equals phi 1 plus phi 2. A middle lantern from engineering. Anti-noise headphones. These devices use the principle of destructive interference proactively. A microphone picks up the ambient noise, say the drone of an airplane engine. A processor calculates the phi field of that noise wave. The headphones then generate a sound wave with the same amplitude but the opposite phase, a perfect anti-wave. When this anti-wave meets the noise wave in the space just outside your ear, destructive interference occurs. The two phi fields sum to, ideally, 0. The noise is cancelled before it reaches your eardrum. This is superposition as a tool for active erasure, a direct technological application of the interference production rule. A far lantern from quantum physics. The double-slit experiment. This is the canonical, profound example. A beam of particles, electrons, photons, even large molecules, is sent toward a barrier with two narrow slits. Behind the barrier, a detector screen records where they land. If you close one slit, you get a single-slit diffraction pattern, a broad blob. If you open both slits, you do not get two blobs. You get an interference pattern, a series of bright and dark fringes. Each particle, described by its own wave function, a complex valued field intimately related to our phi, goes through both slits. The wave function from the left slit and the wave function from the right slit overlap and interfere on the screen. The probability of detecting the particle, which corresponds to the intensity of the total wave function, shows the classic bright and dark bands. The particle, as a localized detection event, lands only in the bright bands. This experiment demonstrates that interference is not just a property of classical waves. It is a fundamental production rule for probability amplitudes in the quantum dialect of the holophase language. It is interference writing the pattern of reality itself. From the quiet spots in a room to silenced airplane noise to the foundational mystery of quantum mechanics, a universal theme. When two or more wave sentences from the same source or coherent sources occupy the same region, they do not merely add their intensities, they add their phases. This phase-sensitive addition creates a new, rich pattern of enhanced and diminished effect, a pattern that encodes relationships and enables control. What then is the specific language role of interference productions? It is the grammatical rule for sentence combination. It is the syntax that governs what happens when two or more valid wave sentences are spoken simultaneously in the same narrative space. It is not mere concatenation, it is an integration that creates new meaning, new patterns, from the interplay of the constituents. It answers, What is the combined meaning of these two simultaneous statements in the wave language? The core question this part asks about phi is, what is the rule for combining multiple simultaneous wave solutions in the phi field, and what structured patterns in time, space, and intensity does this combination rule generate? We are moving from the grammar of single sentences to the grammar of paragraphs and dialogues. What does this interference rule do in the generative process? It creates complex spatial and temporal patterns from simple components. It encodes information about source relationships, distances, angles, relative phases, into observable intensity distributions. It enables precision measurement at scales far smaller than the wavelength of the probing wave, interferometry. It forms the basis for coherence and collective phenomena, where many waves act in lockstep as one macroscopic field. Now, stability and breakdown. The principle of linear superposition and interference is exact and stable in linear media. It holds as long as the waves do not interact non-linearly, meaning the presence of one wave does not change the medium for the other. It breaks down in two primary ways, through non-linearity and through decoherence. In a nonlinear medium, waves can scatter off each other, generating new frequencies. The simple phi1 plus phi2 rule fails. Decoherence is more subtle and bridges to quantum theory. When a quantum system interacts irreversibly with a large chaotic environment, the precise phase relationships between its possible wave functions are lost. The interference pattern washes out, and the system begins to behave classically. Within its domain, linear phase-stable systems, interference is a perfect, predictable grammatical rule. This brings us to the bedrock of our method, falsifiability. The claim that interference patterns arise solely from the linear superposition of phi-field waves with well-defined phases is a precise, quantitative hypothesis. The central claim. For any two coherent wave sources described by the phi grammar, the resulting spatial interference pattern, fringe positions, intensities, and/or temporal beat pattern will be fully predicted by the calculated phase difference between the waves at each point. Changing any parameter that affects this phase difference, such as the path length to the observation point, the source separation, or the wavelength, will shift the pattern in a quantitatively predictable way that matches the calculation from phi1 plus phi2. A concrete measurement scene, the optical double-slit experiment. We set up a laser, a source of coherent light, meaning its phi field has a very stable phase. The laser beam illuminates a plate with two very fine parallel slits. A distance away, we place a digital camera or a movable photodetector to record the pattern of light on a screen. We measure 1. The positions of the bright fringes, maxima, and dark fringes, minima. 2. The relative intensity, brightness, of the fringes. We know the wavelength of the laser light, lambda, the distance from the slits to the screen, d, and the separation between the slits, d. According to the interference rule, the bright fringes should occur at positions where the path difference from the two slits is an integer times lambda. Specifically, position y on the screen equals men times lambda times d divided by d, where m is an integer, 0, 1, -1, 2, -2. The pass condition, validation. The measured fringe positions match the predicted formula with high precision. If we insert a thin, transparent wedge of glass in front of one slit, we introduce a known additional phase delay. The entire interference pattern should shift sideways by a calculated amount. This shift is measured and matches the prediction based on the extra optical path length through the glass. The intensities of the fringes also follow the predicted pattern from two-slit interference. The data confirms that the total light field is the sum of the fields from each slit, with phase determining the outcome. The fail condition, falsification. The fringes appear in the wrong locations, systematically deviating from the prediction. Or, more fundamentally, no stable interference pattern is formed. Under conditions where the phi grammar demands it, coherent sources, stable setup. For instance, if we use a true laser but see only two blurred spots of light with no fringes, something is deeply wrong. It would mean the waves are not maintaining a stable phase relationship, or that the superposition principle itself fails for light in this setup. In the quantum version, if single particles sent one by one through a double slit never build up an interference pattern over many trials, but instead always form two simple clusters, it would falsify the quantum wave interpretation and, by extension, the holophase model for that phenomenon. Such a result would be revolutionary and would force a complete rewrite of the foundations. This falsifiability ties the beautiful abstract concept of wave combination to the unforgiving precision of micrometer scale measurements. Let's cultivate a practical recognition skill. You can train your perception to see interference logic in any scenario where two or more similar influences or signals overlap, and their combined effect is not a simple sum of strengths, but varies between enhancement and cancellation depending on precise alignment. Listen to the chorus of insects on a summer night. The chirping of many crickets can create a pulsating, beating sound. This is interference in time. The slightly different chirp rhythms of many individuals constructively and destructively interfere to produce a rhythmic swell in the overall volume. Observe the shimmering colors on a soap bubble or oil slick. This is thin film interference. Light waves reflecting off the top and bottom surfaces of the thin film travel different paths. Depending on the film's thickness, which changes across the bubble, the path difference causes constructive interference for some colors, wavelengths, and destructive for others. The result is a pattern of shifting colors that directly maps the film's geometry. Consider the coordination of a rowing team. If rowers pull out of sync, their forces interfere destructively. The boat jerks and loses speed. When they pull in perfect unison, in phase, their forces interfere constructively, and the boat glides smoothly and swiftly. The collective velocity is maximized by phase alignment. Whenever you see a situation where timing is everything, where perfect alignment yields a result greater than the sum of parts, and misalignment leads to cancellation, you are witnessing the conceptual core of interference. You are seeing the importance of phase. We must connect this deeply to our holophase journey. In the previous part, packet generation showed us how to write moving words. Here, interference shows us how those words can rhyme, can harmonize, or can contradict each other to create higher order structure. We haven't added a new force of interference. We've simply applied the most natural rule for combining influences in a linear cyclic field. Add them, minding the phase. From this rule, the universe generates its patterns of stripes, its rhythms of beats, its channels of energy, and the very probability maps of quantum events. If you want to see the full mathematical derivations and exact equations behind this idea, the formal statement of superposition, the calculation of interference intensities from complex amplitudes, the derivation of fringe spacing formulas, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let's pause and feel the significance of our position in Book 9.3. We began with the alphabet, dispersion, learned to form words, packets, and now have learned how words interact to form structured poetry, interference patterns. We possess a complete toolkit for classical wave physics. But there is one more sublime step in this book. What happens when interference is not just a temporary overlap, but a permanent, locked-in state? When countless waves not only pass through each other, but synchronize and act as one giant coherent wave. This is the phenomenon of coherence, the foundation of lasers, superconductors, and the ordered states of matter. In the next part, we will explore how the holophase language writes these coherent fields, how it composes paragraphs where every atom, every photon, sings the same phase in a grand, unified chorus. Before we end, the mandatory zoom out to hold our scope. Interference, for all its intricate results, is still just a consequence of the linear superposition of phi. The fringes, beats, and nodes are patterns in the intensity, which is derived from phi and its derivatives. We have added no new substances or forces. We have simply explored the powerful grammatical consequence of the language's linearity and cyclicity. One field, phi, plus its infinite tower of derivative questions. In this episode, we have journeyed from the first sentence through topological production, knots and braids, and now deep into wave production, where we can write solitary pulses and predict the beautiful, stable patterns born from their union. The grammar is demonstrating its capacity to generate the ordered complexity that characterizes our world. As we conclude, hold the image of the pond with two sets of ripples. The meeting point is not a place of conflict, but of creation. The silent nodes and towering crests are not accidents. They are the necessary grammatical output of the system when two valid wave sentences are superimposed. The universe is this pond on the scale of everything. Light, sound, matter waves, even the probabilities of events are all ripples in the holophase field. And wherever they meet, they write interference patterns. The silent music of constructive and destructive addition, the hidden geometry that guides energy and shapes our perception of reality. Interference is the universe's way of drawing with waves, and we have just learned to read the brushstrokes. Salam and peace be upon you.